Okay, today was an important day, and unfortunately we had the troubles with the technology, and so I want to go through the summary of Chapter 5, which will be important for the exam, that we really understand the big picture of what we did in Chapter 5. So remember from the beginning, we said that calculus is about two fundamental problems. And the first of that is you know how much of a quantity you have at every moment, and you want to know how fast it's changing at every moment. And the second problem is you know how fast a quantity is changing every moment, and you want to know how much of it you have every moment. So my question would be, what have we been working on in the last month? Which of these two, A or B? And so every single person who's watching this should know that we're talking about, in the last month, we've been talking about endeavor B here. The second one, which is you know how fast a quantity is changing every moment. You want to know how much of it you have at every moment. And the first one is differential calculus. And this second one is what's called integral calculus. Okay, so let's do an overview of Chapter 5 here, which is about this. You know how fast a quantity is changing at every moment. And so what is it that we would know that would tell us how fast a quantity is changing at every moment? Well, that's what a rate function does. An exact rate of change function for any value of the independent variable gives us the rate of change at that moment. So here this illustration was for our unloading sand that we've done over the last week a couple times. This is the exact rate of change, and we call that R sub f. And then what would be how much of it you have at every moment? What mathematical thing would give us this information? And you should be thinking, well, that would be an exact accumulation function. So here's the exact accumulation of weight. This A sub f function is the accumulation of weight on the sand according to this rate of change. Slow at first, then gaining speed, then falling off the fastest, then slowing down again. And we see that here, increasing slowly, increasing the most quickly, and then increasing slowly in terms of the weight of sand on the scale as it unloads from the truck. Okay, so the question becomes then, how do we do this? How do we get exact accumulation from exact rate of change? And we, over the course of a couple weeks here, or 3 weeks in fact, been working on this journey of how to do that. And so from exact rate of change, you should be thinking, well, we're going to get an approximate rate of change function. So these blue constant rates here are trying to replicate our real rate function. So it's only approximate because, of course, it's a different function, but it has constant rates that are trying to be like the real changing rate function. And we got that function as rf of left of x, created this, what we call a step function, or a constant rate of change approximating function. And from that, the reason we wanted that is because with constant rate of change, we can build accumulation. We can build accumulation because we can use m dx. And then accumulating over many intervals, we're going to add up every m times change in x, m times change in x. We're going to add all those up. So we're going to sum up the changes in y. We're going to sum up dy's. And that's going to look like this. We're going to sum up rate times change in x. And here I'm just using change in x to generically mean the change of x of a completed interval or the current interval. So just a generic change in x, right? So r times the change in x gives us a little change in accumulation, and then we're going to sum all those up to get the total change in accumulation. And this was the underlying premise of our approximate accumulation function A. So based on these blue constant rates, we could build an approximate accumulation function, and it'll be linear like this, piecewise linear, because each constant rate will result in a linear increase, in this case increase, in the amount of weight of sand. So then what was the key from getting to approximate accumulation to exact accumulation, this nice curve that's the exact accumulation function? Well, it meant making our changes, our intervals, smaller. Okay, and actually, so incorporating realistic moments. Okay, so we're going to make delta x very small, and that's going to represent realistic moments. Remember, we said a moment is an interval over which we could assume that the rate of change is constant. So for these large moments, it's not realistic, right? It's not a good approximation to the rate function. But for small delta x, we get lots and lots of teeny little constant rates that do a good job representing this. And so if we make delta x really small, then we say we want to make it small enough so that this constant rate function, which I'm showing in blue here, is indistinguishable from the actual rate function. And when you have that, then your approximate accumulation function will be indistinguishable from the actual accumulation function. So this was the journey we've been on to get exact accumulation from exact rate. From exact rate, you start with approximate rate of change function made up of constant rates, and then you use those constant rates to total up small amounts of accumulation, and that was the basis of the long accumulation function that we worked on. And then once you let those intervals get very small, that approximate accumulation function converges to the exact accumulation function. Okay, so because we did all that heavy lifting, we did all that work to develop the exact accumulation function, we've earned the right to a fast track from exact rate to exact accumulation. And that fast track from exact rate to exact accumulation is integral. Okay, integral is where we start with exact rate and immediately we can do exact accumulation. Okay, so that is this expression right here. We start with exact rate. This integral expression that we build out of exact rate gives us exact accumulation. And we see the principles that we talked about in that long journey from exact rate to exact accumulation. We see all those principles embodied here. We have their exact rate function times a little change in our independent variable. So all of that then is a little bit of accumulation, or a little dy, because that's essentially m dx. And what are we going to do? We're going to sum up all of those dy's, the little changes in little accumulated amounts, which each accumulated amount was calculated by m times the change in the independent quantity. So m dx plus m dx plus m dx, but a zillion of those all added together, starting from the starting value of the independent variable a to the final value of the independent variable x, and that's what our accumulation is a function of. It's a function of where we want to stop accumulating. Okay, so if you let that x increase, then we get the accumulation function. We get how much of it we have at every moment. Okay, so that's an overview of chapter 5, and very important that you understand the big picture of what we've been doing. So watch it again, watch this part again, one more time, two more times, whatever it takes to understand this journey that we've been on in chapter 5. Looking just at the rate graph, when is the temperature going to be the lowest? When do you think? So let's talk about this. It starts at 40, and by the time it gets to 4 minutes, what about in the first 4 minutes? When is it the lowest? Right there at 4 minutes, right? It's been going down all this time. So right now it's at the lowest point. And then what about all this time from 4 to 13? It's increasing. What about this amount of increase compared to this amount of decrease? Which one's bigger, the amount of decrease in the first 4 or the amount of increase in the next 9? The increase is clearly more. It's a longer period of time, and the rate is a higher positive in the middle than the rate is low, how negative it is here, right? So not only is it for a longer period of time at a positive rate, but then it's hanging out at a much higher positive rate than this is negative. So clearly, this is going to be higher or lower than the starting temperature of 40 degrees? Higher. It goes down somewhat, but then it's going to go up much more than it went down. So now, in the first 13 minutes, when is it at its lowest? Still around 4, right? This is the lowest temperature. So now it's going to go down again here in the last 2 minutes. But again, that's this amount that it's going to go down according to this rate here for only 2 minutes is never going to bring it back down to this amount that it was at 4. Does that make sense? Because this amount that it went up is a lot more than how much it's going to go down in just those 2 minutes at this rate profile. So that's the reasoning behind, without doing any mathematics, that's the reasoning behind why the lowest temperature occurs right before 4 minutes in this 15-minute time period. Does it make sense? Okay, and then we already sketched it. Okay, we already sketched it. So let's walk through one more time. Let's walk through how we would actually build the accumulation function. So we start with RT. And what do we need next? So what are we going to need? So we're going to start with an exact rate function. What are we going to need next? In order to get, we want exact accumulation. We've got exact rate, we want exact accumulation. What's our next step in this endeavor process? Yeah?
Slap an integral in front of
No. We're going to talk through the process we've been doing the last 2 weeks. So, yeah, we'll get to that eventually. That's direct, right? But we want to talk through the whole process again. Yeah?
We're starting where we're ending.
Well, I'm talking about the process of building an accumulation function. How do we build an accumulation function from scratch? From scratch. Yeah?
Break the x-axis up into different intervals.
Okay, we need a partition of moments, right? And then what are we going to do with those partition of moments? We need another function. What's the next function we're going to make? Nope. Yeah, someone saying it. Approximate rates, constant rates. And we're going to get that from left, right? So by pinpointing the left side of every interval, we can build a constant approximating rate function from the exact rate function. And that looks like this. I've got delta t of something like 2 minutes at a time. Okay, and then, so that's this rate function, this approximate rate of change function, the blue one. Because we can't build approximation, we can't build accumulation without constant rate of change. We want to use MDX. We need constant rates. All right, so from the constant rates, then we can build this, which we worked on, right? The accumulation function, right? So from the constant rates, we can build the accumulation. We can graph that. This is approximate accumulation based on those constant rates. Okay, and then how do we get from the approximate accumulation function? How do we get to exact accumulation? Right, we're going to actually go from these very large moments to make them very realistic moments, right? Small moments, and every time we make our moments smaller, we get a better approximate rate function, and therefore we get a better approximate accumulation function every time we make them smaller. Okay, so then how small is small enough? I'm going to turn off the original rate function. Okay, so you can still see that that's made up of constant rates. Maybe. Okay, so there is changes of 0.02 minutes. And you can see all those constant rates for those moments of 0.02 minutes are doing a very, very, very good job of replicating our real exact rate function, and therefore the approximate accumulation function is looking like it's converging on a curve, right? It's converging on a curve. Okay? So here is then, so then the next thing for you to do is you are to write the function that gives the exact temperature in the fridge at any time x minutes after 3 p.m. Just do number 5. Can you do number 5? So can you write, what is it that, how do we express now the exact accumulation function that this is converging on? Can you do it? Can you express it? See if you can do it. Number 5. So this is what many of you wanted to do from the start. So now what? Go for it. Okay. Okay. You want 0 to t and r of t dt? You got the problem. You're making the one error that we talked about, right? So he wants to do an integral. Is it an integral? Yeah. Yep. The integral from what to what? Okay. So either a to, or in this case, would be 0. So I have a set at 0. So I wrote it as a to x of our RT function, and I used u this time. Okay, that's fine. So RTU du from a to x. You see what you did? Yeah. You can't match them, right? You can't match those variables. But then if we want it to be the temperature in the fridge, we got to add 40, right? We're gonna, because that integral is gonna, when x equals a, that integral at the starting value, it hasn't accumulated anything yet. So the integral will always start at 0. But if we know that temperature at our time 0 is 40, then we've got to add 40. Okay, so now if I graph that, let's see if 0.02 moments gives us a accumulation function indistinguishable from the exact one. So now I'm going to graph that function you just wrote. I'm going to graph it. So there's the integral function. So let's zoom in, say right here, and see how we did. Pretty dang close. So if you wanted to be closer, you could, but we're looking here at what point? This is 0.2 degrees, so this is, you know, in the hundredths of degrees off, okay? In the hundredths of degrees off. So you could still make delta x even smaller, and then you'd be even closer, okay? But from this view of the whole 15 minutes, it sure looks the same, right? It sure seems like all those ordered pairs would be the same. It's working hard because it's doing all those little things one at a time. Okay? Okay, so now we've got our exact, so what was the process to build the exact accumulation function? We started with exact rate of change, and from exact rate of change we did what? No, we didn't do accumulation. From exact rate of change, what did we need? Constant rate of change. We need the approximating function, right? That's what I'm showing over here with a very small delta x. I'll make it big again. This is this journey we've been on, from exact rate to approximating rate. Constant rates, right? Constant rates that are trying to pretend to be the exact rate. And from those constant rates, gave us the ability using mdx to build the A function, right? The A function, the approximate accumulation function. And then, if we make our moments small or realistic, then that approximate accumulation function converges on the actual accumulation function. That's the process. That's the process. Okay, so we got a couple more questions here. Express the temperature in the fridge at 3:10 p.m. How can we express the temperature in the fridge at 3:10 p.m.? A of 10? RT of 10? Plus 40. Okay? It's AT of 10. A sub t is our exact accumulation function. Okay? A sub t is our exact accumulation function. If we evaluate it at 10, we're going to get the temperature at 310. And that, look, so GC is telling me it's 42.8 degrees after 10 minutes. Okay? What about, so how else could I express that? So besides AT of 10, how else could I express that temperature at 10 minutes? Besides the number, of course, right? So the number is a third way. But there's another way to express that temperature at 10 minutes. Well, it would just be in terms of the rule, right? So you could also express it as 40 plus integral from 0 to 10 RT, I'll use U, du. So all three of those are expressions of the temperature at 10 minutes. Okay, next question. Express the change in temperature from 301 to 305 and do that in two different ways. Go for it, we got a couple minutes. So express the change in temperature from 301 to 305 in two different ways. Express that change. Anyone got one way to do that? Express the change in temperature. Yeah. AT5 minus AT1. What do you think? I'm going to put it in GC. GC knows what my AT function is. Oh, no. So AT5 minus AT1 says negative 0.73. Does it make sense? Does that make sense? Why? What's happening mostly between 1 minute and 5 minutes? Decrease, right? So you get mostly decrease. There's a little increase at the end of that time period, but mostly decrease. Therefore, the temperature in that 4 minute period went down 0.73 degrees. Makes sense. Another way to express that, this change. How could we express the change in temperature from 1 minute to 5 minutes? Yes, sir?
I got AT of 5 is equal to 40 plus. I just pretty much took the plus AT of 1 and subtracted it.
Okay. Yep, so you could write out this twice and subtract. But I want to do it more concisely than that. I want to use, yeah.
Would it be 40 plus
But that would just be the temperature at 5 minutes, not the change from 1 to 5. Yes, sir. Okay, right, but we can still do it even more concise than that. Yes, sir. Right. Yeah, so you can start integrating at 1. Start integrating at 1, so it would be the change from 1 to 5. So it would be, and here I'll just use x. Now that we just have all numbers there, x is fine. Why? Because this is the change in our quantity as x changes from 1 to 5 at this rate. So that'll give me the change in temperature starting at time 301, ending at 305. So let's put that in GC. So watch. Look, hold on. I'll put in the integral from 1 to 5 of RT dt. And look, it's the same, you get the same thing. You see that? So I can express it as, in function notation, final value of the quantity minus initial value of the quantity, or I can just make it its own integral, accumulating starting at 1 to 5 at that rate. At that rate. And you get the same change. Okay, so I had I wanted to go over I wanted to do more today. Sorry. But this is most of it. So I may put an addendum on the video. I may sit in my office and talk to you for 15 minutes on the video and do a little bit more. Okay? This is all fair game for the exam. Okay? Yeah. Not from here to here. Let's say, is the temperature decreasing here? No. So where's the largest increase? From where to where? It's going to give you the largest increase. There. Because it's still going up. The temperature's still going up at a positive rate. Okay. There's this, yeah. It's as close as you can pick it off. Yeah. So like 3.8 and 13.2. Yeah. Question?
Yes. Okay, so for part 7,
Yeah.
I was thinking about it in terms of like dy equals mdx. So would it be correct to just label it as the rate times the change in x, which is for us? So RT of x times
What's the rate?
RT of x. Because we don't know
Okay,
it.
but what MDX is what kind of rate?
Oh, okay, that's constant.
Yeah, MDX is constant rate of change. And the whole point here is from 1 to 5, your rate's changing. So that's why we need to use the integral.
But like, yeah, okay, so the interval, that would still technically be correct, but it's just not labeled right.
What's that?
Because, okay, wait. So I'm trying to think. This is in constant rate, so it wouldn't work like the other problems, where, do you remember when the answer was like 122.2, where we had a constant rate, and we could find the number?
Right. Because it was the integral of a number, so that's constant rate of change. So then you can just take that number times how much rate it's
But
changing.
this isn't constant,
This
so...
rate is constantly
Right.
changing.
Right.
The rate's constantly changing.
Okay, okay,
Yep.
thank you.
You bet.
Questions. I'm a little confused in how we know that the temperature is going to be the same at that point, 6 or 7 minutes. Is it
It's
because
just a
it's
guess.
balancing out?
It's a guess. It's kind of, yeah, we're just kind of eyeballing. We're just thinking, okay, so it's going down at this rate profile here, and now it's going to start going up. So it's kind of like a balancing act, right?
Okay.
So somewhere around here, the amount of increase is going to be the same as the amount of decrease that you had there.
Okay.
It's just eyeballing.
Alright.
But it's not going to be here. That's going to be more increase than that was decrease.
Okay.
It's not going to be here. That's not enough increase to balance out that decrease. So somewhere around 7.
Okay. And then, so the highest temperature would have been at that point then, because this is accumulating all temperature
Yep.
here? Okay.
Yeah, because this amount of accumulation of temperature, because the rate is higher and the time frame is longer, the amount of, it's going to go up here is going to be more than the amount it went down here.
Okay. Alrighty. Cool. Thank you.
Hello.
I had a quick question.
Yeah.
So the reason why that
So,
red function,
I need to ask you a question. Yeah.
the reason why that red function is the same is because it shows the change from 1 to 5.
What's that?
The reason why that red function, the integral 1 to
Yeah.
5, is because it shows a change from 1 to 5, right?
The change of the temperature starting at 1, ending at 5. And so does this. Final minus initial. Do you see? And this is showing a change, the accumulation or the change, starting at 1, ending at 5 at this rate. Well, that's the change in temperature.
For number 8 is
Yeah,
the
number-
same as number 6, like meeting.
The same, but just your endpoints now are going to be 3.8 to 13.2. So you could do a sub t of 13.8 minus a sub t of a sub t of 13.2 minus a sub t of 3.8 would be one way to represent that change. Or you would do the integral from 3.8 to 13.2 of r sub t.
So when it's saying largest increase, not talking about this, but talking about the rate, the increase in rate.
No, largest increase of this quantity. How are you going to get the largest increase in this quantity? Where is that going to be? The largest increase of the quantity according to the rate. The largest increase in temperature.
So does that mean it's only in one place?
We want to figure out what interval within this 15 minutes is giving me the biggest increase in temperature.
Okay.
So is that from 0 to 8? Is that from 2 to 4? Is that from 6 to 12? So what interval in between 0 and 15 is going to give me the largest increase in temperature? Right. Do you see what it would be?
I mean, because
Tell me what's happening to the temperature. Tell me what's happening to the temperature. Go. Tell me what's happening. What about now?
decreasing,
What about now?
decreasing,
What about now?
decreasing,
What about now?
starting to increase, increasing, 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 decreasing, decreasing.
Okay, so that's perfect. Now where's the largest increase in temperature? From 1 to 1. Okay. Which span of time gives the largest increase in temperature?
But wouldn't that just be at one point? Because
An increase, the largest increase in temperature. What's happening? Do it again.
decreasing, 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 increasing, increasing.
The temperature's increasing now. It's increasing. It's increasing. It's getting bigger. The temperature's increasing. The temperature's increasing. The temperature's increasing. So what's the span of the largest increase in temperature? What?
Starting like 3.8
3.8
to
13.2.
13.2. Which is asking from which point to another point it's having the
But
largest.
you have to represent that largest increase.
Okay.
So you first have to figure out what span of time gives you the largest increase. Then the question says, represent that largest amount of increase.
Okay.
So what would it be? So how would you represent now the largest increase in temperature?
My wife's first thought was maybe I did something wrong or I'm not following that one.
3.8 to 13 point.
But from 3.8 to 13 point is not an increase in temperature. That's just a change in time. You have to represent the increase in temperature. So how would you represent that increase in temperature over that time period?
So from 0 to 1.
All you're doing is talking about x values. How do we represent a change of the quantity?
Or you just
Integral.
integral from one point to another.
From what?
From 3.8
3.8
to 13 point.
of what function?
8 sub t.
No. Integral is always, you never do the integral of an accumulation function. It's always going to be the integral of the rate function. Yeah. The other way you could express that change would be a sub t of the actual temperature in the fridge then minus the temperature then. So a sub t 13.2 minus a sub t 3.8 would be the other way to express that.